So, as I said the other day, I'll wait for Cole here. As I said the other day, the plan was to sort of cover Newton's three laws, sort of in general, and then a little bit more in depth. Now, depending on how things go, I might get through two of them today, sort of make up a little ground. There's not a whole lot to this one. In fact, I'm kind of thinking about maybe changing up my method of teaching and maybe just doing them all in depth over 3 days instead of sort of over 4.
Why don't we go in depth?
Say again?
It's like we said we're going to go through all 3 of them, right?
Yeah.
So if we just go
Yeah, every day.
one of them in depth
I don't know.
each day.
Just because I've done it that way for a long time. I guess it just takes effort to revise. Whether it's better that way or not, it's tough to say. Anyways, this is what I have today. So you'll notice that I'm now skipping through the third law. That's because the second law is kind of the mathematical one that kind of leads into the problems. Okay, so I'm sort of skipping, but I have a reason. Okay? So let's begin here. You've got exactly what I've got there. Zane, are you going to join us today?
First one. Alright. What's the first one?
Objects in motion stay in motion, objects at rest stay at rest, right? That's kind of the short version of it. So the third law is, which one?
Every action has an equal and opposite reaction.
Exactly. Is that what you're going to say, Junior, or you're going to ask something?
Talk about the second law.
Yeah, I'm going to skip over that one. We're going to come back to it because that's the one that leads into the word problems. So I'm going to come back. And really, like, what makes the first one the first one? There's nothing special about it that makes it first, really. So, yep. Don't worry, I haven't forgotten. Okay, so a force is a push or pull that acts as upon an object as a result of its interaction with another object. Forces result from interactions. As discussed in lesson 2, some forces result from contact interactions. Normal force, frictional force, tensional, and applied forces are all examples of contact forces. And other forces are the result of action at a distance. Oh, that's something that we haven't talked about just yet, I don't know. Have we? I can't I can. Action at a distance. Can you just highlight that? Because that's something that we're going to get into when we get to the next unit, where we start talking about fields, force fields. Action at a distance, right? Like if I want to knock Brett's coffee off the table, I'm going to have to touch it. I won't. I have to touch it. I can't use my Jedi skills to do it, right?
You lift the other side of the table.
I could, but I still have to apply, I have to be in contact with something, right?
Okay, yeah.
But if I want this balled up piece of paper to fall out of my hand, I just let it go.
So the Jedi don't use lots of force.
I'm still working on my Jedi training.
You one with force.
So there is this action at a distance interaction. Gravity, electrical, magnetic forces all result as of action at a distance. More on that in the future. According to Newton, whenever objects A and B interact with each other, they exert forces upon each other. When you sit in your chair, as you all are, your body exerts a downward force on the chair. Do you feel it?
Yeah.
No, you don't.
Yeah.
You feel the chair.
Chair's bending.
Ben.
You feel the chair exerting a force on you. You can't feel the force that you exert. Pardon me?
So the floor would feel it.
Yeah, I suppose. Well, the floor feels the force of the chair on it, right? Yeah. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There are two forces resulting from this interaction, a force on the chair and a force on your body. These two forces are called action and reaction forces and are the subject of Newton's third law of motion. Formally stated, Newton's third law is, for every action there is an equal and opposite reaction, and I'm going to ask that you add the word force. Equal and opposite reaction force. Now, the key words are equal and opposite. Now, it doesn't matter how many times you say it, equal and opposite. I'm going to ask you questions, and you're going to tell me that the forces are unequal. I don't know why. People, they can regurgitate it, they can memorize it, but they don't really understand what it means. And I'm going to be tricking you a few times throughout this period. The statement means that in every interaction, there is a pair of forces acting on two interacting objects. The size of the force on the first equals the size of the force on the second. The direction of the force in the first object is opposite to the direction of the force in the second object. Forces always come in pairs. Equal and opposite reaction force pairs. Equal!
What's equality?
Equality?
Equality.
Oh, equals. Oh, that should be 2 words, right, Leo?
Oh, equals.
Equals the. It's just 2 words, yeah. Missing the space. Examples of interaction force pairs. A variety of action-reaction force pairs are evident in nature. Consider the propulsion of a fish through the water. A fish uses its fins to push the water backwards, but a push on the water will only serve to accelerate the water. Since forces result from mutual interactions, the water must also be pushing the fish forward, propelling the fish through the water. The size of the force on the water equals the size of the force on the fish. Equal!
I think we understand.
You'd be surprised. Size of the force in the water equals the size of the force on the fish. The direction of the force in the water backwards is opposite direction of the force on the fish forwards. Again, repeating, I'm getting tired of saying it, for every action there's an equal in size and opposite in direction reaction force. Action-reaction force pairs make it possible for fish to swim. Consider the flying motion of birds. A bird flies by use of its wings. The wings of a bird push air downwards. Since forces result from mutual interactions, the air must also be pushing the bird upward. The size of the force in the air equals the size of the force on the bird. The direction of the force in the air downwards is opposite the direction of the force of the bird. Why do I feel like I'm repeating myself?
You are.
It's because I'm repeating myself. For every action, there is an equal in size and opposite direction reaction. Action-reaction force pairs make it possible for birds to fly.
Sweet, we get it.
That doesn't make sense to me though, because like, why would it be equal? I feel like it has to be more in order for it to go anywhere.
Right.
Sorry.
Well, yeah,
Oh, no.
when it's going,
Sorry.
Yeah.
when it's going up, it would have more. But like if it's like flying at the same level, it would be the same, right?
Equal!
I mean, he said it about 8 times.
Okay, if it was more.
What Ty and Olivia are referring to is they can't understand how you can, like, there's got to be, right?
No, I got it.
The problem is that those forces are equal, but it's got to do with mass and it's got to do with how much force is on you. So, Ty's saying the bird does this, right? How come the bird goes up? Okay, well that force of the air on the bird is more than the force of
Gravity.
gravity.
Oh, so it's not the
Right?
force of the first one.
It's not the force that if the bird pushes down in the air pushes up the same amount of force, and that force up
Has to be
is
more than
more than the force of gravity. How come when I do this, I don't go up?
Because you got more mass and not very effective wings.
Exactly. And the force that I produce on the air, which is equal to the force that the air is pushing up on me, does not overcome the force of gravity on me, because I'm so massive.
Does it do any force though?
When I do this?
Yeah.
Sure.
Oh, it does.
You can do it in water and you'll go through it.
Yeah.
Oh.
I mean, the density of the air is pretty low, right? I don't have hollow bones like a bird. I'm weighing a little bit more than a bird, right? So, does that make sense, Pat?
Oh, you're
Yeah,
good.
yeah.
Yeah. And I'm going to keep coming back to that because it takes several goes around for people to understand.
I understand
Yeah, you think you do.
I can
that.
Here, I'm going to give you one more.
search.
Hear that one?
I'm always leery when students tell me to search for something.
So it gets like crazy, but she'll skate.
No,
That's not
sword.
Which thing is then the
I'm
fly?
sorry, I don't
The
know.
pink one? Flamingos?
No.
Birds that fly have hollow bones.
Oh,
Fly.
why the chicken can fly?
Who you?
Search it. Search it.
How do you spell that?
Tutuyu. What is that? What is that?
You?
No, do you? Search it. What is
You
that?
can't even say that, never mind searching.
What is that? Why the chicken can't fly?
Why the chicken can't fly?
Yeah, because they have wings and.
They do have wings.
Chickens do fly.
Penguins fly, okay? They're flying feathers.
Let me finish with this.
Okay,
Well, then we'll look at it.
Your biggest chickens can fly and they can fly.
Yeah? Okay, I'll look it up. Stay with me here.
Really?
Chickens do fly just one set. Put them on the other break together.
Are you serious right now?
Yeah.
Really?
I want to search it.
Like, penguins fly.
Well, they don't really have wings, they got flippers.
They can fly around like, and look like an eagle, that should be perfectly fine.
Okay, let me finish, then we'll look it up. Consider the motion of a car on the way to school. You all came to school today. A car or bus is equipped with tires that spin. As the wheels spin, they grip the road and push the road backwards. The tires push the road backwards.
Oh, no.
How come the road doesn't go backwards?
Because it pushes it forward.
Massive.
No,
Come on, forward.
because the road is attached to the earth, which is pretty massive, right? And big masses don't accelerate very easily.
So
We need a
if
lot of force.
Like if a bus
Oh, that's right, because you're off that.
go on top of the mud,
Yeah,
he
they would push
backwards.
push that backwards, exactly. Leo?
So,
Go, Leo.
so the Earth has those, what do you call, like inside the Earth, that shapes?
The plates, the tectonic plates.
Yeah. So if everybody,
Oh, yeah. Push, yeah.
move.
Everyone
No.
got on one, it was just.
I saw
like,
it.
If we had a
everybody
lot,
gets in their cars and
yes, if we had a lot more everyone, we could. Like,
theoretically.
there's not enough people to do it.
Oh, that would be what we move the
You're a little bit ahead of the game, but my car's like not one. Think about, okay, here's a scale model of the globe, right? Okay, so you look at Canada, how big is Canada,
Really big.
right? Well, I mean, it's a big country, right? But I mean, in comparison to the globe,
Oh, not very big.
like, it covers how much, what percent of the globe? Would you say Canada?
One or two.
5%?
Three.
I would say even less.
3%.
Okay, say 3%. Well, you ever looked out the window and see how much empty space there is?
Yeah.
There's a lot of people in Canada, but there's a lot more other stuff, right? So you think about, if you put all 7 billion people on this globe, what would their mass be compared to the mass of the Earth?
I'm saying Canada.
No, less than 3%, right there? There is no way.
Did you know that we could all fit in the same Texas if we were
I
at?
believe that,
at New York City?
yeah. Yeah, I believe that.
You know, I saw one where we could all fit in small. They're all like, I watched a video on it. It was like,
Well-
and it's like they literally have a city above the city.
You think about-
This one lady had a kid, she's 23 years old, and her kid's 5 years old, and this kid never touched the ground. It's like,
Right?
like, she's
Yeah.
23 years old, she's never, her and her son never touched the
Yeah,
ground.
yeah.
Because they got a city above the ground, so why they gotta go down the ground? They got everything, they got schools, they got stations, everything, roads all over, it's crazy.
Think about, like, in these squares, these tiles here, I can't see the edges, right? That's about a square foot, right? So everyone, you could probably, if you had to, you could squeeze into a square foot, right? So I mean, even
I wouldn't do that.
maybe a foot and a half,
Yeah, that would be.
okay? Yeah, okay, so we'll say a foot and a half, right? Even 2 feet, right? 2 square feet. So I mean, if we have 25 people in here, 25 square feet is 5 by 5.
Wow, that's not much.
That's not a lot, right? 5 squares by 5 squares. You can put 25. We'll say 2 feet. So then you got to go to 50 square feet. That's 5 by 10.
Wait, so
Right.
it would be
So-
7
many people?
7 billion people. Right. So if everyone needs a square foot, that's 7 billion square feet, right? If everyone needs 2 feet, well, that's 14 billion square feet.
How many square feet in a mile?
There's
Feet a mile.
how many feet in a mile? 3.
That'd probably cover like 4 miles.
I don't know. I never remember that conversion.
Smush everyone together.
You guys can figure that out. We got way off topic here. Thanks, Leo. Thanks. We got way off topic there.
Yeah, you're welcome.
Okay. Anyways, consider the motion of a car on the way to school. A car is equipped with wheels. Oh, I know how we got off topic. As the wheels spin, they grip the road and push the road backwards. Since forces result from mutual interactions, the road must also be pushing the wheels forward. The size of the force on the road equals the size of the force on the wheels of the car. The direction of the force on the road backwards is opposite the direction of the force on the wheels forward. Again, for every action, there is an equal in size and opposite in direction reaction. Action-reaction force pairs make it possible for cars to move along a roadway surface. Okay, let's see if you get it. I don't have clickers.
Hey, that's a law, right?
Yeah, it's a law. It's Newton's law.
Yeah.
It is a law. And remember,
You never did a thing on the wall?
huh?
You never did it?
What are you talking about?
That's like physics, straight physics. Oh, I had it. Never mind.
Where's your,
You can draw the wall. What?
Physics. Oh!
How did it see you there?
Yeah, Mr. Bennett.
I've never seen that.
Never seen that?
Brazilian black magic. What the heck is this?
Oh my god!
Every action has a reaction. You never saw that?
I've never seen that.
Wow. You must have.
I've never seen this. Why
How
are
do
you
you
lying
feel
about
about
it?
it?
What?
How is that?
No, it's you lie. It's
You guys probably
super
better
wrong.
than that.
Super wrong.
Yeah, I know. You know.
I've never seen this.
No?
How does it work, you know?
So, yeah.
This is very cool.
Cool.
So, you have thing right here. So the pressure,
Oh, the air!
and you put the, like, the
What?
with the pressure
Yeah.
go up.
You saw this
So
little hole in
the
it?
pressure doesn't let the pen go fall.
I wanna see this.
Makes sense.
What? Well, how much you see? I mean, you can see it from where you are.
That's trippy!
Yeah, that is wild. You know what? I'm gonna add that to my.
So, put the hole against the wall.
Remember those pictures I
And
did?
then, and then you push. There's pressure inside the pan.
Yo.
Hold up,
Oh, okay.
Why not
So
open?
Push all the air out and then it sucks into it.
you're sucking the air out. Is that what you're doing?
Oh, I don't have that.
Yeah, I know. Yeah.
If you didn't tell us how it worked, you could do that.
Wow.
You, oh, Leo, you could say it's magic.
Oh, I'm gonna do that. Like,
You could say.
you know what? I'm gonna use that in my what goes up must come down.
Jealous.
Yeah!
You're jealous now because Leo is no more than you.
Leo, you just make like me.
Oh, see?
But you know what? I gotta find. You know what?
Leo deserves a treat or something.
He does. Correct answer? C. How many people said B? While driving down the road, a firefly strikes the windshield of a bus, makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus, and the bus hits the firefly. Which of the two forces is greater? How many times did I say? Equal.
Well, it's just because the mass of the bus is bigger, right?
Exactly. Trick question. Each force is the same size. Equal. The fact that the firefly splatters only means that with its smaller mass, it is less able to withstand the larger acceleration resulting from the interaction. Besides, fireflies have guts, and bug guts have a tendency to be splatterable. Windshields don't have guts. They're very solid, right? But the forces are the same. Equal. Equal and opposite. Think I'm going to try to trick you again, even on the test? Yeah. But it's not a trick. It's a do you understand?
Not a great one.
Here's question number 2. Read it up here.
Leo.
Are you signed in today? I heard you say you didn't get a chance to answer.
Brandon, do you mean dragonfly?
Dragonfly, firefly, mosquito, it doesn't matter what it is.
Yeah, I explained already.
Are they the green light?
Dragonfly's a big one.
Dragonflies. Moving on, it doesn't matter what kind of insect it is. Insect.
No.
For years, space travel was believed to be impossible because there was nothing that rockets could push off of in space in order to provide the propulsion necessary to accelerate. There's no air to push off.
No.
This inability of a rocket to provide propulsion is because space is void of air, there's nothing there, so rockets have nothing to push off of. Gravity is absent in space. Space is void of air, so there's no air resistance in space. Or nonsense, rockets do accelerate in space and have been able to do so for a long time.
Is this what actually happened or what they thought was the problem?
No, this is which one of these things is true.
This is like history though.
No, it's physics, which is true. People thought you couldn't accelerate a rocket in space because there's nothing to push off of. is this, which one of these
Just answer
things,
the question.
which of these is
They're
true?
wrong.
I thought they all were like, true, but
Which is the most true then, Leo?
Why is there only 2 questions?
Maybe that's all I got prepared? I don't know. I probably have started to make this into a clicker thing and just haven't finished.
That's okay.
I apologize.
That's okay.
Mika, what do you say? What's going on here?
He doesn't want to tell you.
yeah, see,
Sad face.
glitched out.
Ah.
Broke the-
What is going on? Correct answer is D!
I told you.
Of course rockets accelerate in space. Okay? Now, can you explain? Because like people think, okay, like if I'm on rollerblades and I push, right? Well then I'll go backwards, right?
Yeah.
Like if I push on the table pushes on me. Because how come I don't go flying backwards? I'm pushing on the table here. How come I'm not going backwards?
Because of the friction. The friction.
There's a friction. There's more friction on me than the table pushes on me, right? Now, if I push really hard, I can start sliding backwards, right? But if I'm wearing rollerblades, or if I'm on ice, I'll slide backwards, right?
Yeah.
But what's going on here with these rockets? It's a common misconception that rockets are unable to accelerate in space. The fact is that rockets do accelerate. There is indeed nothing for rockets to push off of in space, at least nothing which is external to the rocket. But that's no problem for rockets. Rockets are able to accelerate due to the fact that they burn fuel and they push the gas in a direction opposite the direction with which they wish to accelerate. So the rocket is actually pushing the gas molecules out,
They just push over here.
and the gas molecules push the rocket forward. It's really kind of conservation of momentum.
That's on fire.
Yeah, it's not pushing off of the ground. People always think they see the rocket, right, like this, and then it's, they see that, right? They see that part, and they think that it's pushing on the ground. The ground's just there. It's not doing anything, right? Like the ground doesn't push on the rocket because they're not touching, are they?
Oh, I
Aren't they
question
equal?
that. So,
It's just
like,
over
you know how like jets like land on carriers and stuff?
Yeah, like,
So it's
okay.
And like those things like hold up behind the jet.
Hey, how does
Yeah,
And like when they turn on, I think does that, it's like supposed to help it take off.
take off?
Hey, Mr. Ben.
Well, they hook in with basically it's like a big elastic band.
Yeah, but they also have that thing that goes up behind it for the.
Oh, like the wall, right?
We got the wings.
No, I know what he's saying. The aircraft carrier puts up a wall and it,
What's that for?
that's a good question, I don't know.
Must push off a little bit.
Unless it's just so like no one gets burned, maybe, or.
Yeah, it could be.
Slow down.
Like it's like sitting like on an aircraft carrier.
Yeah, it might have to do with that. It might have to do with keeping the boat. It's a good question. Let me investigate that call. That's a good one.
They take off with such force, you don't want it blowing halfway across the thing, because there's people walking around working, you don't want it.
Yeah, maybe.
Because there's stuff there, there's other planes, there's.
Yeah.
I want it to be so possible.
I've never actually thought about that. I don't even have ever actually seen it. So
But it's got the same study, same thing, it's not pushing off the wall.
no, it's not.
Yeah.
No,
That's why-
it's probably a protection thing. I would think so.
This man, clearly you've never watched Top Gun.
Not a long time. Haven't been to the danger zone for a long time though. Oh, I got question number 3. You lied to me. Cool.
I don't know, it said finish on here.
Okay. Well, there's number 3.
Well, it's in our
Rockets.
The rocket pushes all the gas out the backs, right? And the gas molecules, all that exhaust, and the whole molecules push the rocket forward. And there's very little air resistance.
It's like when you open the thing over the balloon and let it fly.
Yeah, same idea. Right? All of the air is pushing out.
But why is it fire then?
Well, it's combustion. It's combining with oxygen. It's really a controlled explosion, really.
What?
I mean, I don't understand all of the rocket science, but I mean, it's a controlled explosion that pushes that exhaust gas out.
Yeah.
Yeah. So it's a large release of energy.
Yeah, it doesn't make sense.
Okay. Many people are familiar with the fact that a rifle recoils when fired. This recoil is a result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward in the bullet. Consistent with Newton's third law of motion, the bullet pushes backward upon the rifle. The acceleration of the recoiling rifle is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, the same or equal size as the acceleration of the bullet. A, B, or C. What? It's B? You said, Mr. Bennett, that it was always equal.
Just forget it.
I said equal force.
I told you I could.
Equal force. This says the acceleration of the recoiling rifle is smaller. Why is the rifle acceleration smaller? Because it's bigger.
100.
Bigger mass.
I knew that.
You got that one right. You're doing well. That one's a trick. Because I do that equal thing over and over, right? I also don't, I know you noticed that I didn't use the word equal here either.
You did, you said it after.
I did, I said it after, I tried to trick you, yeah.
You didn't check me.
Right, you're a genius.
It's my job, trick kids. The force of the rifle equals the force of the bullet, yet the acceleration depends upon both force and mass. The bullet has a greater acceleration due to the fact that it has a smaller mass. Remember, acceleration and mass are inversely proportional. Okay. Number 4, in the top picture, below, Kent Budget, pause for laughter.
Can't budget.
Oh, I'm going to get started.
Get it? Because he can't budget?
Thanks.
Yeah, he spends all his money, can't budget.
No, I thought you meant like he couldn't budget.
Yeah, I know.
Okay.
Just checking him.
He's pulling upon a rope that is attached to a wall. In the bottom picture, Kent is pulling upon a rope that is attached to an elephant. In each case, the force scale reads 500 newtons. Kent is pulling. Which one of these is true? With more force when the rope is attached to the wall, with more force when the rope is attached to the elephant, or the same force in each case. Did I start it?
We can't sell these on backwards now.
What?
Got the same horse. This is force.
Wait, can you read it again?
In the top picture, he's pulling upon a rope that is attached to a wall. In the bottom picture, he's pulling upon a rope that is attached to an elephant. In each case, the force scale right there reads 500 newtons. So Kent is pulling with more force when the rope is attached to the wall, with more force when the rope is attached to the elephant, or the same force in each case. It's a trick answer, yeah.
It's A, of course. It's C.
It's A.
Okay.
Well, I sure hope the answer's here.
Olivia, let's go.
The clickers are awesome because they make kids answer.
Remember that.
If you sign into it, they can account it.
Correct answer is C, same force. What does the thing read? Kent is pulling with 500 newtons of force in each case. The rope transmits the force from Kent to the wall or to the elephant and vice versa.
What was your math here? What math are you doing?
Since the force of Kent pulling on the wall and the wall pulling on Kent are action-reaction force pairs, they must have equal magnitudes. Inanimate objects such as walls can push and pull. You ever run into a wall? It hurts. Why? Because it applies a force to you.
But it's on the road.
It doesn't move because it's big. Oh, looks like I got 2 videos here.